section 5.4, orthogonal diagonal of symmetric matrices. So the first questions here, they ask you to orthogonal diagonals the matrix. Orthogonally diagonalize the matrix by finding the orthogonal matrix Q. So here is our goal, because we need to satisfy this theorem, which is says the Q transpose times the matrix A times the Q matrix is going to be the diagonal matrix D, which is the diagonal row for this matrix is going to be the eigenvalue. It's a theorem. You can check the slides. So first of all, we need to find the Q matrix. How are we going to find the Q matrix? So the first thing here is the matrix A with 6, 3, 3, 6. And we're going to find the first thing, the eigenvalue and eigenvector. So the determinant of A minus lambda I, determinant of, here is the matrix A minus lambda, and here is the I, 1, 0, 0, 1. That means it's going to be 6 minus lambda, 3 minus 0 is going to be 3, and 3 minus 0 also, and 6 minus lambda. Find the determinant for this one, which is multiply these two elements, 6 minus lambda, 6 minus lambda, and minus 3 times 3, which is going to be 9. So now we're going to distribute here, minus 9, then move the lambda squared here, combine the like terms, is going to be 27, because 36 minus 9 is going to be 27, and minus 6 is going to be 12. Factor this, which is going to be determinant equals 0. That means lambda squared minus 12 lambda plus 27 equals 0. We're going to factor this one, 93. That means we have lambda equal 9 and lambda equal 3. This is the first step to find the eigenvalue and eigenvector. I'm going to start with the smallest eigenvalue. So when lambda equal 3, the determinant of A minus 3i, that means we're going to plug in 3 here. So 6 minus 3 is going to be 3. Here is a 3, 3, and 6 minus 3 is going to be 3. With 0, 0, by reduction, we're going to reduce this one by using reduce row echelon form. It's going to be 3, 3, 0, 0. You're just going to multiply by negative, or you're going to multiply by negative, add with this one, convert this one to, it's up to you. Which one you're going to do, it's fine. The main thing you have to, here's the first entry, this is 0. This one is going to be already 0. So here is the reduced 4. That means 3x1 plus 3x2 equals 0. 3x1 equals 3x2, divide both sides by 3. So x1 is going to be minus x2. So this is the, we're going to find the first eigenspace. We're going to let x2 equal t. That means x1 equal negative t. So the eigenspace is negative t and t. We're going to let t equal 1 is going to be the span, which is negative 1 and 1, which is the same thing as the base, negative 1 and 1. I'm going to assume that this one is v1. Now I'm going to go back, and when lambda equal 9, so a minus 9i, that means you're going to plug in 9 here. So it's going to be 6 minus 6 minus 9 is going to be negative 3, and here's a 3, and it's going to be 3 here, and 6 minus 9 is going to be negative 3. The same thing, we're going to, by reduction, we're going to convert to reduced row echelon form. You can just add these together, so it's going to be 0. Add these together, is going to be 0. So negative 3x1 is going to be equal to 3x2 plus 3x2 equals 0. That means x1 is going to be equal to x2. We're going to let x2 equal t. X1 is going to be t. That means the eigenspace is t and t. We're going to let t equal 1. Now this is the span, which is the base is 1 and 1. I'm going to let this one equal v2. Until now, I didn't do anything to find the matrix Q, but I did the steps to find the eigenvalue, and then we're going to find the eigenvector or eigenspace, the base, and I'm going to use V1 and V2. The V1 and V2 always going to be orthogonal vectors. That means when you multiply or find the dot product, when you do the dot product between V1 and V2, the result is supposed to be 0, which is -1 times 1 is going to be -1 plus 1 times 1. So -1 plus 1 is going to be 0. So that's, if you want to check, V1 and V2 is supposed to be orthogonal. That means the dot product between V1 and V2 equals 0. These two vectors are orthogonal by this theorem. That means the dot product is going to be -1 times 1 plus 1 times 1, which is equal 0. We need to normalize these two vectors. How are we going to normalize these two vectors? So we can get orthonormal vectors, because the Q, the columns for the Q matrix are orthonormal. That means orthogonal, and the length for each column equal 1. Like the Q matrix equal Q1 and the Q2. Q1 with the Q2 are orthogonal. That means the dot product equals 0. And on the same time, the length for each vector is going to be equal 1. That's why it's orthonormal set, or orthonormal vectors. Now, the length for V1 is going to be -1 squared plus 1 squared, which equals square root of 2. The length of V2 is going to be 1 squared plus 1 squared equal square root of 2. That means to normalize, it's going to be Q1, 1 over the length of V1 times V1, 1 over square root of 2 times the V1 -1, 1. Here is the first vector. Q2 is going to be 1 over the length of V2 times V2, 1 over square root of 2, 1, 1. And here is the second vector. So our Q matrix is going to be Q1, Q2, which is this matrix. Now, if you check the dot product between this Q1 and Q2 is going to be negative, positive is going to be 0. And the length for each column here, which is each vector, is going to be 1. This is the theorem if you check the slides. So a Q inverse is the same thing a Q transpose. That means Q inverse times A times the Q. So you don't have to find the inverse for the Q. You already equal Q transpose. That means equal Q transpose times A times Q, which is equal the diagonal matrix. The diagonal matrix, the diagonal row is going to be equal the eigenvalue, which is 3 and 9. And it's a symmetric matrix. Always these elements equal 0. So if you multiply Q transpose times A times Q, the result is going to be this one, which is the matrix D. So if you want to check, do the multiplication between Q transpose times A times Q, the matrix D is going to be exactly the same thing. We're just going to put the eigenvalue here, and that's it. But if you multiply Q transpose times A times Q, is going to be, here is the result, 3009. So you're going to do exactly the same thing with example 2. Let's solve example 2. You see example 2 and example 3, they are exactly the same. I did both these to make this easier for you. So you just have to do it step by step. So example 2, our matrix A is 4 square root of 5 square root of 5 and 0. So we're going to do exactly the same steps. The first thing, because our goal is to find the matrix Q, the matrix Q. So the first step here, determinant of A minus lambda I, determinant here is the matrix A minus lambda 1, 0, 0, 1. That means going to be 4 minus lambda square root of 5 minus 0 and square root of 5 and negative lambda, which is equal. You're going to multiply these. So negative lambda times 4 minus lambda minus square root of 5 times square root of 5 is going to be 5. Then we're just going to write down from the highest one to the lowest one. So lambda squared minus 4 lambda minus 5 equal. Factor this one, lambda minus 5, lambda plus 1. Yes. Now the determinant of A minus lambda I equals 0. That means these two parentheses equal 0. So lambda equal 5 and lambda equal negative 1. Now next step, always I'm start from the smallest one, negative lambda equal negative 1. So when lambda equal negative 1, be careful here. When you plug in negative 1 here, it's going to be 4 minus negative 1. That means it's going to be 5. And here's square root of 5, square root of 5, negative 1 is going to be positive 1. The same thing by reduction. How are we going to do the reduction here? You're going to divide this one by 5. So it's going to be square root of 5 over 5. Then you're going to minus this one. So this one is going to be 0. This one is going to be 0. And this one still 0. That's mean by the reduced form is going to be this one. That's mean x1 plus 5 square root of 5 over 5 x2 equals 0. So x1 is going to be negative square root of 5 over 5 x2. We're going to let x2 equal t. That means x1 is going to be negative square root of 5 over 5 t. So the eigenspace, here's the eigenspace. We're going to let t equal 1. So the span is going to be, or the base is going to be negative square root of 5 over 5 and 1. You can simplify this one by write down 1 over square root of 5, or you can keep it like this. It's up to you. I'm going to let this one equal v1. Because by using v1, I can get the q1, v1. I need to check v2, and the dot product between v1 and v2 equals 0. That means these are orthogonal vectors. Now lambda equal 5. So a minus 5i is going to be with the 0. That means you're going to plug in 5 here. 4 minus 5 is going to be negative 1. Here's 5. Here's the square root of 5. Square root of 5. And here is negative 5. By reduction, it's going to be 1 negative square root of 5, 0, and 0. That means x1 minus square root of 5 x2 equals 0. So x1 is going to be square root of 5 x2. And x2, we're going to let x2 equal t. That means x1 is going to be square root of 5t. So here is the eigenspace. Let t equal 1. So we're going to get square root of 5 and 1. This one is going to be v2. So by plugging, by let t equal 1, so it's going to be square root of 5 and 1. This one is going to be v2. And that's what I did here. So the base is going to be square root of 5 and 1. This is going to be v2. So the same thing, we're going to check v1 and v2 are orthogonal. That means if you multiply v1 by v2, the result is, if you do the dot product between v1 and v2 is going to be equal 0. Now we have orthogonal vectors. We need to normalize these two vectors. So the length for the first one is going to be negative square root of 5 over 5 squared plus 1 squared. So it's going to be 5 over 25, which is 1 over 5, plus 1 is going to be square root of 6 over 5. Then normalize the length for the V2 is going to be square root of 5 squared plus 1 squared. So it will be 5 plus 1 is going to be square root of 6. Then a Q1 is going to be 1 over the length of V1 times V1. 1 over the length of V1, which is 6 over 5, times the first vector, negative square root of 5 over 5, and here is 1. We're going to multiply, is going to be negative 1 over square root of 6, and the second one is going to be square root of 5 over square root of 6. You can type it like this, or you can type it like just 5 over 6. Both is going to be right. A Q2 is going to be 1 over the length of V2 times V2. So it's going to be 1 over square root of 6 times V2, which is square root of 5 and 1. Multiply, so it's going to be square root of 5 and square root of 6. And here is 1 over square root of 6. The same thing here, you can type it as square root of 5 over 6. Now our Q matrix is going to be Q1, Q2, and here is the matrix. This matrix is the columns or the vectors for these two matrices. The dot product between Q1 and Q2 is going to be 0, and the length for each one is going to be 1. So this is the diagonal matrix. That means if you multiply the transpose for this matrix times the matrix A times the Q, we're going to get the matrix Z, which is equal -1 and 5 as an eigenvalue and 0 here. The diagonal matrix always, the diagonal row always going to be the eigenvalues. So let's check this example. So we got it right. If you look to example 3, I already solved this example, but it's exactly the same thing here. So the first thing what we did here, here's the matrix A, 8, -2, -2, and 5. We're going to find the eigenvalue. And again, be careful when you do the first step, because you're not going to figure out it's a mistakes until you find the result. So always be careful here when you find the eigenvalue. Determinant of A minus lambda I is going to be the determinant of 8, -2, -2, and 5 minus lambda with the matrix I. Then you're going to get this matrix, multiply 8 minus lambda and 5 minus lambda, and -2 times -2 is going to be 4. So it's going to be -4. Combine the log terms, is going to be lambda squared minus 13 lambda plus 36. You can factor this one by lambda minus 9 and lambda minus 4. Determinant equals 0. That means these two parentheses equals 0. So lambda equal 9 and lambda equal 4. The first lambda, well, lambda equal 4. I did the first lambda because they asked me here to write down the smallest lambda value. How much is going to be the base or the span for this one. So A minus lambda minus 4i with the 0 is going to be this matrix. That means I'm going to plug in 4 here. So 8 minus 4 is going to be 4. -2, -2, 5 minus 4 is going to be 1. By reduction, you're going to get this matrix. That means x1 minus 1 over 2 x2 equals 0. So x1 is going to be half x2. Here, what I did, let x2 equal t. That means x1 is going to be half t. Our eigenspace is half t and t. Here, I don't want to work with the fraction, so I'm going to let t equal 2. So it's going to be 1 over 2 times 2 is going to be 1, and here's 2. This is the first base. So here we're going to type the lambda equal 4, 9. And here we're going to plug in 1 and 2. The first base. Now, let's check with the second one. When lambda equal 9, so A minus 9i That means we're going to plug in 9 here. So now 8 minus 9 is going to be -1, -2, -2, and 5 minus, we're going to plug in 9. So 5, yeah, plug in 9 here. 5 minus 9 is going to be -4. Now y reduction is going to be 1, 2, and all zeros here. That means x1 plus 2x2 equals 0. So x1 is going to be negative x2. We're going to let x2 equal t. x1 is going to be negative 2t. So here's the eigenspace. Let t equal 1. So the span of the base is going to be -2 and 1. So here is -2, and here we're going to put 1. Now the next step, we're going to work to find the Q matrix. V1 equal 1, 2, and V2 is going to be -1 and 1. So the base is -2 and 1, which is this is the V2. Again, we can check V1 and V2. The dot product between V1 and V2 equals 0. That means V1 and V2 are orthogonal. We need to normalize V1 and V2 to find orthonormal vectors. So the length for V1 is going to be 1 squared plus 2 squared. It's going to be 1 plus 4 is going to be 5. The length of V2 is going to be -2 squared, and 1 squared also is going to be square root of 5. That means Q1 is going to be 1 over the length of V1 times V1, 1 over square root of 5, and 1, 2. It's going to be 1 over square root of 5, 2 over square root of 5. This is the first column on the matrix Q. The Q2 is going to be 1 over the length of V2, so it's going to be 1 over square root of 5, -2 and 1. So it's going to be -2 square root of 5, 1 over square root of 5. That means our Q matrix is going to be Q1 Q2, which is here we get. The dot product between these two vectors is going to be 0. The length for the first column equal 1. The length of the second one equal 1. So this is orthonormal vectors. That's what I'm going to focus on. Q transpose, if you multiply Q transpose times the matrix A times the Q, the result is going to be the diagonal matrix, which is the diagonal row is going to be the eigenvalues 4 and 9. That means we can plug in Q and D here. We got this one right. So example 5, and I think example 6 is going to be exactly like example 1, 2, 3, but you're going to take 3 times 3 matrices. So again, example 5 is exactly the same steps. You're going to find the eigenvalue, then the first span, the second one, the third one. Then you have to find the matrix Q. Example 6, exactly the same thing. Example 7 is different. Now we have to find the spectral decomposition. For example 7, so here is the spectral decomposition, which is lambda 1 times Q1 times Q1 transpose, and lambda 2 times Q2 times Q2 transpose. This is the spectral decomposition. And if you check the slides, you're going to find how the rules, these two rules with the theorem. If you add these two, lambda 1 Q1, Q1 transpose plus lambda 2 Q2, Q2 transpose, you're going to get exactly the same matrix A. So now, but our goal for this example is to find lambda 1 Q1 Q1 transpose and lambda 2 Q2 Q2 transpose. Let's check that. So here is the matrix A. So our goal is, first of all, we're going to find the eigenvalue and eigenvector. So let's work with finding the eigenvalue by finding the determinant of the matrix A minus lambda I. The same thing here is going to be -1 minus lambda, and here is 7, 7, -1 minus lambda. Then it's going to be -1 minus lambda, -1 minus lambda, minus 49. Combine the log terms. It's going to be lambda squared plus 2 lambda minus 48 equal. Factor it. Here is what we got. The determinant equal to the 0. That means these two parentheses equal 0. In this case, lambda, let's say lambda 1 or lambda 2. Lambda is going to be equal -8, and lambda is going to be equal 6. So they tell you here, choose the large lambda here and the smallest lambda here. That's why I start by finding lambda equals 6. So, which is the large value, because here's -8. Plug in 6 here. So it's going to be -7, 7, 7, -7. 0, 0. By reduction, here is the reduced form. That means x1 minus x2 equals 0. In this case, x1 equal x2. We're going to let x2 equal 2. That means x1 equal t. x2 equal t, sorry. That means our eigenspace is going to be t and t. Let t equal 1. Here is the span, which let's say this is the base. 1, 1 equal v1. So now I'm not going to go ahead and use the second eigenvalue because I need to find the q1. So right away here, I'm going to find the length for this vector. The length for this vector is going to be 1 squared plus 1 squared equals square root of 2. To normalize this vector, we're going to say q1 equal 1 over the length of v1 times v1. So 1 over square root of 2 times 1, 1. Here is what we get. q1 transpose is going to be just this column is going to be a row. So if you multiply lambda 1 times the q1 times the q1 transpose, it's going to be 6, 1 over square root of 2, 1 over square root of 2 times the q transpose, and here is the result. So that's the spectral decomposition with lambda 1. So we're going to type 3, 3, 3, 3. We're going to do the same thing with the second one. So when lambda equal -8, that's what's going to happen. We're going to plug in. We're going to get 7, 7, 7, 7. By reduction, it's going to be 1, 1, 0, 0, 0, 0. That's mean x1 plus x2 is equal to 0. So x1 is going to be -x2. We're going to let x2 equal t. So x1 is going to be -t. That means our eigenspace is going to be t, -t. Let t equal 1. So the base or the span is going to be 1, -1. This is the second vector. And you can check that by doing the dot product between v1 and v2. The result always going to be 0. That means these two vectors are orthogonal. Now the length for v2 is going to be the square root of 1 squared plus -1 squared, which is going to be the square root of 2. Then normalize v2 by 1 over the length of v2 times v2. So 1 over square root of 2 times 1 -1 is going to be 1 square root of 2 over square root of 2 -1 over square root of 2. Q2 transpose is going to be, this column is going to be a row. Now lambda 2 times the Q2 times the Q2 transpose is going to be -8 times this one times this one. So here is the spectral decomposition for the second. Lambda, when lambda equal -8, So we're going to say -4, and here is 4, and 4, -4. And to check this one is the right two matrices. So that's what I did here to show you that means these two matrices are right, because if you add the first special decomposition with the second one, the result is going to be the matrix A, which is our matrix. So that's what here I just want to show you. That means if we add these two matrices with the lambda one with this one, 3 minus 7 is going to be -1, 3 plus 4, so 3 minus 4 is going to be -1, 3 plus 4, 7, 3 plus 4, 7, and the 3 minus 4 is going to be -1. This is the matrix A. That's mean 100% this one is going to be right. There we go, we got it right. So this is important example. We are going to do the same thing. I think the next example is exactly the same numbers. So if you look to example 8, the same matrix, just have to write down the eigenvalues here and the span, then the first decomposition, the second one, and that's it. Example 8, the same thing, example 7. So here's the eigenvalue, and the span is going to be 1, 1, and the second span is 1, -1, and the first decomposition is going to be, this is all 3, and the second one is going to be -4. The diagonal is negatives, and here 4 and 4. You have to, so because we have exactly the same matrix, so it's going to be the same result. And we found the eigenvalue, we find the first span, the second span, and the special decomposition. For example 9, now we need to find a symmetric matrix 2 times 2 with eigenvalues λ1 and λ2 corresponding to the orthogonal eigenvectors v1 and v2. So they tell you these two vectors are orthogonal. So here is the way, or here is the key to work on this example. If you remember, we have the theorem. It says Q transpose times A times Q is equal to Q transpose times A times Q, which is equal to the matrix G. That means if I reverse this one, D, so here's the thing, A equal Q transpose times D times Q. That means if I took the multiply this one by Q, then multiply by the inverse. So we're going to cancel these two. Is going to be A equal Q inverse DQ. Q inverse equal the transpose. That means A equal Q transpose times D times Q. So that's what I'm going to use, because our goal is to find the matrix A. So what I have here, I have V1 and V2, and I have λ1, λ2. So by using the first vector, to find the Q1, and we're gonna find the Q2. From V2, we're gonna find the Q2. And then I have the transpose and I have Q. I have the eigenvalue λ1 and λ2, which is the matrix D. So now I already know the matrix D is going to be -1, 0, 0, and 4. Because the diagonal for the matrix D is going to be the eigenvalue, and the rest of the elements is going to be zeros. So now V1, the length of V1 is going to be 1 squared plus 1 squared is going to be equal square root of 2. Normalize V1, we're going to get Q1, 1 over the length of V1 times V1, equal 1 over square root of 2 times 1, 1. So here is a Q1, The same thing with V2 is going to be 1 squared plus negative 1 squared, which is equal to square root of 2. Now Q2 is going to be 1 over the length of V2 times V2. It's going to be 1 over square root of 2 times 1 negative 1. That's what we get. That's mean our matrix Q is going to be 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, and negative 1 over square root of 2. The transpose, the first row is going to be the first column, the second row is going to be the second column. And here is the matrix D, which is the same thing. Now A is going to be Q transpose times A times a Q times D times the matrix D. So if you multiply Q transpose times D times the Q, you're going to get the matrix A. And that's our goal to get. If you look, they're telling you 2 times 2 symmetric, 2 times 2 matrix. Here is the diagonal. This is symmetric because here we got it's exactly the same element. That's it for example 9.